Hello, welcome back to our text classification tutorial. So today I would like to continue from my previous text classification tutorial. So in the previous session we have talked about support vector machines and we have used the quantitative text models. Now today we would like to use a different package, which is using e1071 package. So if you haven't watched the previous tutorials on text classification, I had a full tutorial on. So this was part 15. So today's session will be about support vector machine using e1071, which will be part 16 of our video. So if you haven't watched, I recommend watching the previous tutorials. Then it will be clear what kind of data I'm using and which algorithms, which are packaged. Also some theoretical intuition about the algorithms are already described, at least for naive Bayes and support vector machines. The intuition, the theoretical intuition were already described. And in the previous video, I talked about support vector machines using the quantitative text models package, which is a very fast linear kernel. So today I would like to proceed from that, but I will use a different package, which will be e1071. So I will turn this down and I will simply proceed to our tutorial today. So for that, the first thing we have to do is we have, let me probably remind you what kind of data we have. So if you remember in the previous sessions, we were loading this package, ggpro to caret and bib2bdf to remember the bibtext data that I have. And I have text data, which is extracted from PubMed, biomedical literature. So it's mainly about COVID and SARS, and we would like to classify whether an abstract is about COVID or is about SARS. That's what we have been doing in the past few sessions. So we read and finally we have implemented naive Bayes and also support vector machines, and we have seen some of these TF-IDF, and we have implemented these algorithms using the simple frequency. That means words are simply counted or they are weighted using the TF-IDF weighting method. And we have seen two different algorithms. That's naive Bayes, the Bayesian classification using the simple frequency data or the TF-IDF version of the data, and also we have used a support vector machine from the quantitative text models, and we have simply implemented either the TF-IDF version of the data or using the simple frequency version of the data. So today we will proceed just using the e1071 package. So the e1071 package is I think e1071. This number is actually I have it's a room number. So it's kind of a weird name for the package. Usually you don't hear these kind of names. This is my first time to actually to have, for SVM package we expect to be SVM or something, but it's e1071. But I think the author of this package was living at 1071, room number 1071 or something. I'm not exactly sure, but you can find out if you are interested into this. So that's the first thing that we need to do. So once we do that, so we load the library. So once we load our library, so it seems my file is a little bit busier. So if you remember, we are using this thing called the document featured matrix. So this is when we were pre-processing our data, we were using quantitative text models package. Quantita, the pre-processing. So we were tokenizing and doing all those stuff. So that one we were using this document featured matrix. So if you remember, we have let's say in the feed, maybe we can check also the dimension of train. So we have train document feature matrix. So it's a special kind of data form, which it's not exactly like data frame or something, but the e1071 package requires your data to be structured in a data frame format. So for that, we have to convert this train and test data frames document feature matrix actually into a format that's suitable for this package. Otherwise, it will not run for you. So the first thing that we need to do is that means we need to convert this data frame. So let me call it train data frame. And then the first thing what you need is you need to convert this train data frame into the train dfmat. That was train document feature matrix, and then we need to convert it to data frame. So quantita provides us this function convert to def, convert to function, and this will easily convert it to us. Now we also need to do the same for the test data frame. If you remember in my previous video, I was using the match data frame because I was matching it to the train data frame, so that the algorithm will not be the prediction will not have any problem to they have to have the same structure. So let me call that data frame, and then the same I will do to data frame. So now I have to run this, and I have to check the structure of these data frames. It will take a little bit of time to convert this format, but once you have converted that, we need to check how this data frame looks like. Maybe I pause the video, and so now the data frames are already converted. So let me check how they look like. So let me simply see the head of this data frame, and so if we check the head of the data frame, these are really big data frames. I mean, it's really does lots of variables, so it may take a little bit of time to open. Actually, instead of looking at the head, I would prefer to view this data frame. So the view is better because if we look at the head, because we have so many variables, so it may not be a good idea to look at the head. Instead, it's better to have a look at how the data frame looks like. So that's how our data frame looks like. So you see the doc ID is included as one of our variables. So the doc ID, we don't need this to be included in our data frame. So we have to filter this out because these are the ID. So we will not put this as part of our variable. So we will need to remove this the same in the test data frame and also in the train data frame. And then the rest of all of these will be the variables that we will use in our prediction. So this will be all the X variables that we will use for the training. But this part of the data frame we have to exclude because this is coming from the doc ID identifier from the quantita data processing, because we are converting the document feature matrix into the train data frame. So that's why this part of the document feature matrix is also included in our data frame. So to do that, we just need to remove the first column and then leave the rest. That's what we need to do, both in the test and in the train data frames. So let me replace this. Train data frame will be we just need to remove the first column, so and then the rest will be fine again. So again, for the test data frame, I will again remove that doc ID part of the column. So -1, which means the first column of the data, all except the first column. That's what this -1 does for us. So if we go back and view the train data frame, so we will not see that doc ID in our. There you go. This is how our data frame looks like. So this is a train data frame. So all X variables, they are all our variables that we need. The coronavirus disease and all of these features. Actually, 11,348 features. They are all in our training data frame. But if you remember, the first one was doc ID. So we have already removed that. So let me close this so that. And then now we have our X and Y. I mean, our, all these features, they are our X variables. The next thing is we need to define our Y variable. So the Y, if you remember, the Y for the test is train include. I mean train include. Yeah. So it's train include. So if you remember, we were defining it as include and exclude. I mean COVID and SARS. So if you let me show you the table how this looks like, or we count them. So if we count, 357 of them are COVID and SARS are 300, roughly 50-50, like 58, I mean 48, 52 or something. So roughly very well balanced. This is actually train, not test. Train, but that's our Y variable. But otherwise, you can also simply use this in your support vector. We can simply use the train. So the second thing that we need to use is we need to train SVM function. We need to train support vector machines using the e1071 package. So what the e1071 package offers is this function called SVM. So let's see how this SVM function looks like. You can simply ask R to give us the detail of this function, and we will have an idea of how this looks like. Yeah, so this function, SVM function, is a support vector machine function. So SVM is used to train and support a support vector machine, and it can be used to carry out trivial regression and classification. So you can simply define whether it's you are doing classification or regression. You can simply define it, or I think the default is classification. But if you are doing regression, you can define that. So here are some examples where we can have. So the first thing, you need to define a formula. That's y to x. Then you give a data. Then if you have any omit or something, pretty much similar to the other functions like linear model, LM, or something, or some other function that you may know. But we can see the first argument is a formula, and that's like the way you define your x and the y variable. And then you give a data argument, or you simply give the x and the y. So you don't worry about the data argument. And finally, if you do scaling, feature scaling, you may do feature scaling. In our case, we don't do feature scaling. We will simply use the TF-IDF version of the data, or simply the non-TF-IDF version of the data. We are not using TF-IDF in this case because this is actually this is mainly the TF-IDF. So I must have made a mistake. So because it's TF-IDF, so instead I will have to use again for this one TF-IDF version of the data. I think it's better to use the non-TF-IDF because if you remember in our previous model, the non-TF-IDF version of the data was performing very well. So we just focus on the non-TF-IDF version of the data. Yeah, so you define the formula, you give the x and the y variables, and you do feature scaling if you need, like centering. Centering. There are many feature scaling techniques that you can do, but we are doing text analysis, so we are not going to do any feature scaling. But it might be it's one of the important parts of doing machine learning if you are dealing with different data sets. But we are just doing text mining, and we already have a count data. We are not going to scale our features, but you can have a look. And the type is actually you can define classification, or if you are doing a support vector machine regression, so you define it as regression, otherwise a classification. And there are also additional arguments that you can do. The kernel choice, if you remember, we were talking about kernels in the part 14 of our video. So if you remember, there are many different kernel choices: linear, polynomial, radial basis, sigmoid. But these are the kernel parameters that you can do in if you are using e1071 package. Otherwise, the other kernels like hyperbolic, hyperparabolic, or tangent or something. There are many different kernels. So e1071 doesn't cover all of them. But if you have to do a different kernel choice, then you have to either define it yourself, write the function yourself, or you have to look for any other function which might do other kernels. Otherwise, these are actually the kind of very common kernel choices. We don't use degree, but if you are using polynomial function, you may have to define the degree. In the gamma, there are other parameters that you have to define also. That's gamma. So this gamma parameter it's a regularization parameter. So if you are for all kernels except linear, then you have to define the gamma function, the gamma parameters, like from 0, 0.1, 0.0 something. So you define multiple values and you give it into C. We'll see that when we are tuning support vector machines. And also you also do cost parameters. I think this one you can also do it for polynomial and sigmoid. I don't do it often. I usually mainly use cost and the gamma in the kernel, and it usually works very well. And these are also additional parameters that you can choose. There's also class weights that you can use, and there are additional parameters like hash size, tolerance. There are so many many different parameters that you can use to tune your support vector machines. And this probability is very important. If you would like to do like a ROC curve, then you need to set this probability as true. Otherwise, if you set it, probability is false. So if false, the support vector machine is faster. So it will not be. I mean, it usually calculates the probability, but it doesn't. It internally changes them into classification, like the hard labels, like COVID or SARS or something, depending on or your outcome, maybe positive, negative, or something. But otherwise, if you set this probability as true, then you will let the algorithm to calculate the probability, and then finally you can use that probability to do ROC curves and like. There are so many other functions. I advise to look the function of the package and the tutorials, and also the PDF version of the package, so you can have detailed explanations. And these are the authors, David Meyer, so he's author of the package. So now what we need is we need to tune our support vector machine. We are not tuning in the beginning. I just want to give you a small overview how SVM should be defined, and the next part will be tuning. But now let me just do a quick training. So let me define how much time. Let me say how much time this will take. So let me just take system time. So this system time actually is to take the current time. So if you really want to calculate how much time your algorithm is taking, so this is my time now, 21:49, 51. So it's Central European time. But then you write everything here at the end. You write sys time minus the original time, and then you can see the difference, how long the training algorithm takes. So we already have the x variables. So the x variables will be all the train df. So that will be my x train, and the y variable will be my train include. So that will be my y, and then after that we simply define our algorithm. So let me call this sigmoid, maybe linear. Let me call this linear, maybe SVM linear, and let's see how we define it. So we are training SVM linear. So the first thing we need in SVM linear is we need to define x, and we need to define y. We need to define x, we need to define y, and then we need to define our kernel choice. So basically we are training linear support vector machine, so that means our kernel choice is linear. And then let's do the cost. We can ignore gamma, and let me just give the cost function as 10. And now x is we have already defined x, and the y would be, we already defined again y. So and then you don't need any other parameters. You just run this. But if you would like to tune the model, that means you need to give the gamma and the other values, and you can give it like let's say if the cost parameter would be like, if you are using the cost c into you give it like a 1, maybe 5 or something. So you give multiple different values, and your SVM will try to tune the model. So the last thing we need to do is define. So let's say how much time this should take to complete. The previous one. So let's say system time minus our initial time, which is time. So now after that we simply run all of this and see how long this will take, how it works. So SVM linear, then we take everything. So we wait a little bit until it trains and see. Maybe it's a good idea to pause the video. So I will just pause it. Yeah, there we go. So our SVM, the training, it has taken 6 minutes. So it has already trained our model. Maybe if you want, we can see the summary of the model, how many support vectors we had, and things like that. So I simply take summary of our model, and just like the usual. So you see, this is our equation, the way we define our equation, and then you can see what kind of support vector machine type it is. It's a classification, and our kernel choice is linear, and the cost is 10. So we have the cost parameter was set to 10, and the number of support vectors is 671, which is not really nice. And the classes are like 349 and 322, 671 in total, and that's for the COVID 349 support vectors and 322 support vectors for the SARS. And we have COVID and SARS labels. But if you remember, we have our training and row, the number of rows for our training dataset was about 700 something. Train def. Let me simply So we have only 688 rows, but if you see 671 of them are 671 of them are support vectors. These are the number of support vectors, which is almost as high as 688. So this is probably not a good model, because the number of support vectors is a lot. That's one indication that your support vector machine algorithm may overfit. This is obvious because we haven't defined many parameters, so we were simply arbitrarily defining the cost to 10, and we have also simply defined the kernel as linear. Yeah, those kind of stuff. So we haven't defined the gamma and other parameters. So that's why our number of support vector machines is almost as high as the number of training examples. We have. So let's use this model for prediction, and let's see how much it works. So let me just call again my predict function. So pred linear, let me call pred linear, and then we use predict. And once you call the predict function, the first thing is you need to define your model. That's linear, SVM linear, and the second one is new data. For the new data, we already changed the form into data frame, and that's our text data frame. Let me put this down here. That's all. I think that's all we need. Then let me run this, and after that we'll define our tabulator class. Let me call tab class, and after that let me call pred table function and pred linear and test include. So that will tabulate our confusion matrix, our 2x2 table. Then the last thing is let me do conf-mat confusion matrix for our SVM linear. Then for that we use the usual confusion matrix function. It's a little bit slow, the confusion matrix. Then what we need, we can use a tab class here. And then after that we define the mode. As I said, we want to see everything, so we say everything. Once we define that, we can simply see how our prediction looks like. So let me run all of this and see how it worked. Yes, now it has already predicted our test data, and let's see how the performance looks like. So we have the performance accuracy is 81%, and not as nice as we want, but it's still good performance. We haven't defined many parameters. We have arbitrarily defined the cost parameter to 10. We haven't given the gamma values, and so on and so forth. But the linear, as I said, it's text data is considered to be linearly separable. So the linear SVM seems to be, with cost parameter set to 10, arbitrarily to 10, it seems to be working okay. So especially from the specificity perspective, we have achieved 90% specificity, and sensitivity is 73%. And also the precision is quite impressive again, almost 90%. But we can do better. We can do better by trying many different kernels and comparing. Let's say we can define this into sigmoid or polynomial or radial basis function, and then you see which kernel strategy is the best option. For that, we need to tune it. We need to tune our model. So tuning is the next thing that we want to do. So this is just, we are arbitrarily defining our model, just especially from the kernel and the cost. We have also defined other parameters like gamma and other values that you may need. So in this case, this is really quick and dirty SVM. So you can do better, and that's using tuning. So you have to, for tuning, and let's say what you do is you post the post parameter, you give it into C, and then you give here multiple values like that's not what I wanted. So you give multiple values, and also for gamma, you define it with gamma, and you give it into these multiple different options. And the algorithm combines multiple different, let's say gamma 10 with cost 10, and with linear kernel, or gamma 10 and gamma 5, or cost 2 or something, and then the kernel type will be maybe sigmoid, and it combines all of these combinations and finally finds out the best working algorithm. That's how the tuning works. So in the next video, we'll be tuning SVM algorithm using different kernels, and see how the tuning performs better in achieving a prediction performance. For now, thank you, and yeah.